There were some people expressing concern about BJTs and not completely understanding how they functioned, and I thought maybe a video that just kind of explained this whole load line, um, operating region, saturation, cutoff thing might help to tie it together and give you something to review. So what I've drawn here is a not pointing in, or NPN transistor, and there is another video up that describes the introductory stuff. This is hopefully going to be targeted a little bit higher up than that one. The first thing to understand is that these are used for either switches or used for amplifying. Switches is pretty straightforward. I mean, if I were to draw this same circuit as either saturation or cutoff, in saturation basically you have a resistor, and if it's saturated, I guess you just imagine it as a closed switch, and cutoff would be the same thing, but you're looking at an open switch. And really, these are the two ends of the spectrum. And the area we're talking about is this active region in the center, where it's more like a variable resistor. And this is where amplification happens. And one of the big key factors in amplification is what's called beta DC. Beta DC is just how many times bigger is the collector than the base, right? So beta DC could be like 200, meaning that if we had some currents flowing for a current flowing here of 1 milliamp, we have a current flowing here of 200 milliamps. So you can see we're amplifying it. And if I had this current change up and down slightly, this would change the same, but of course would be 200 times bigger. So we're amplifying it. We're getting a magnified version of the small base signal on the collector, right? That's kind of the overview of how this works. The part that kind of starts messing people up a little bit is this whole idea of load line. And I'd like to take a shot at giving that some sort of explanation. If we were to draw a graph that looked like this, and say VCE is here, and IC is up here, right? We'd be able to sort of say VCE, well, if VCE is at its biggest value, well, that means the transistor is open, or down here you're in cutoff, right? So if VCE is very large, you're cut off. In other words, it's an open switch, right? Again, imagine a resistor. If I measured the voltage here, right, and this was, say, 12 volts. If I read 12 volts on the voltmeter, that means the switch is open, which means cutoff, which means VCE is very, very large. The other option, I suppose, is up here, IC. So if the current's flowing, or if the current in the collector is at max, what we're saying then is it's a closed switch, right? So this current is as big as it can be. So those are the two ends of the spectrum. That's as a switch. And what I can do is draw a line between the two and say, well, if one is completely open and one is saturated or completely closed, then this line represents the active region, or the region between the two, where I can kind of have the base signal move up and down slightly and get really big changes in collector current. But of course, if at any time that small base current pushes this to cutoff or saturation, it wouldn't amplify anymore. You'd be at your limits. It's like a car. It can't go slower than stop or faster than max speed. So what we do is we set up what we call bias circuits. And what we're trying to do in a bias circuit is set it up so that sitting idle waiting to amplify, it's kind of sitting right here where there's the current flowing and the voltage of the VCE and the current flowing in the collector are somewhere around the middle of this active region between saturation and cutoff. It has the most room to move these two directions without hitting saturation or cutoff. And the idea being that now I can have a very, very small base signal, right? So the base can produce a very, very small base signal, and I can have a very, very big collector signal come out of the transistor that's not hitting saturation or cutoff, right? Of course, if this was in the wrong spot, we'd be hitting cutoff or saturation if it was up here, right? Long before it amplified or got an identical signal, and you'd lose, this part up here would all be lost. So we're trying to find this active region, and we use bias circuits to set it up, and we do math like in the previous video to try and find out where this, what they call Q point, is on this load line. Right? So what we're trying to do is figure out on this load line, where's that Q sitting idle, and then from there we can figure out how it acts when it amplifies it. And I'm going to show you an example of a bias circuit just to give you a bit of a feel for what we're after here. Oh, that's not what I wanted. There. So an example of a circuit that's used for biasing might be what's called voltage divider. So the idea is I'd like to use one power supply, DC, right, and set it up so that that power supply provides the big power or the big current flow on the collector, and at the same time, if I use two resistors in series like this, and I'm careful about the size of the resistors I choose, I can actually have a voltage here that is my base voltage, or VB. Right, so example, if these resistors were both the same size, I'd have 6 volts in the middle. Right? It's just a voltage divider. So this allows me to set a VB. Once I've set a VB, I can set the current that's flowing through this forward bias, and that gives me the ability to set up my collector currents. And what I'm basically doing is setting up on that load line that we just talked about. If I'm real careful on how I design this circuit, I can set up a Q point where it kind of just sits idle, sits here waiting, and then when a signal gets superimposed, right? You know what a superimposed signal is. It's just, if I had an AC sine wave and I superimpose DC, the whole sine wave just kind of floats at a higher level, right? It just sort of all rides on that DC value. I can superimpose a small signal here on this DC VB, right? So I could put in a small signal here, and I'll show you how to do this in a future video. This small signal here forces this current to change up and down slightly, and causes this current to change up and down, but of course this current will be beta times bigger than IB. So basically beta ends up being my gain, or beta ends up being how many times bigger is the collector to the base, and this is amplification. We have to add a few more pieces, and there's a few different circuits, but these biasing circuits, their role is just to set up this Q point, to just to set up the voltages on the base and the collector and base currents so that it's ready to amplify, and hopefully in the right spot, that it has maximum room to move between saturation and cutoff.